In this video, we focus our attention to the case where our Banach space is an LP space, and we prove a theorem that is arguably the most famous theorem in ergodic theory. It's due to Birkhoff. It has slightly stronger assumptions than the von Neumann-Yasuda theorem, but it also has, in many ways, a stronger conclusion. So what this theorem looks at are contractions on LP that actually arise from operators that are contractions on both L1 and L infinity. So if you're a contraction on both L1 and L infinity, by interpolation, you're contractions on all of the LP spaces. And the theorem is not just concerned about contractions on all LP spaces, it also focuses on positive contractions, that is, operators that preserve positivity in the sense of LP spaces. And what that means is that if you have two functions and f is greater than g in the sense that f of x is greater than g of x for almost every x, then this is preserved by the operator. Tf of x will be greater than Tg of x for almost every x. What's the quintessential example of an operator that falls under the scope of the theorem? Well, the composition operators that we care about in ergodic theory, concrete ergodic theory. So if you take T of f equal f of phi of x, for phi a measurable map between omega and omega, then you have something that is clearly positive, and you have something that's also clearly L infinity contractive. Now, for appropriate measure, you can also show that it will be L1 contractive, but you want specific choices of measures for that. Now, if you have such an operator, and it satisfies the assumption of our theorem, the conclusion of Birkov theorem is that the convergence of the Cesaro averages to the projection onto the null space will happen for every f, not just in norm, but also almost everywhere. Now, that's very useful in practice, because what this tells you is that you can look at a single value of omega in your space capital omega, and you look at the orbits of that dynamical system started at that value omega, and from that you infer global properties of the system, right? Typically we would be able to prove in concrete application that this projection is actually just taking the average of f. So you derive properties about the functions acting on every point in your space as a variable from looking at an orbit for a single point. So this is helpful in practice, and notice that for that to be helpful, to be able to approximate the space average of f by taking time averages in that way, that's really the idea of ergodic theory. It's very important that we don't just use a abstract theorem and take a subsequence that converges almost everywhere from our sequence that converges in LP norm. Because if we don't know what that subsequence is, then we really have no idea how many times and how long we need to observe our system for in order to approximate its statistical properties. So that's the idea from a practical point of view of really preferring an almost everywhere convergence to a convergence in the sense of some sort of mean, in the sense of an LP norm, which is the reason why von Neumann-Yasuda theorem are often called mean ergodic theorem, as opposed to Birkhoff, which is a pointwise ergodic theorem. So we will prove this theorem. We won't give the original proof, we will give a proof where we derive it from our theorem, from our mean ergodic theorems, from our theorems in norms due to von Neumann and Yasuda. And the key thing we need in order to prove that theorem is the next lemma, and there's a very general principle behind that lemma that comes from harmonic analysis, so ergodic theory. The two fields are very closely connected, and this lemma tells us that when we look at the supremum of the quantity we want to converge, this supremum has good LP properties. So taking such a supremum here is what we call taking a maximal function. This particular one is called the ergodic maximal function associated with T. And what we are proving here, if you remember, is a weak type PP inequality for that maximal function. So there's a general principle here that if you have good control on the supremum of the quantity you want to prove convergence for, you will be able to deduce convergence from appropriate control of suprema. So let's do that first. Prove the appropriate weak type PP estimate for the maximal function, and then we'll derive theorem 14.6 from lemma 14.7 and theorem 14.5. Okay, so let's prove this maximum inequality. Let's give ourselves a lambda and let's give ourselves an f in LP. Now I'm going to define mk to be, let's call it mk lambda, to be the sum of the tj of absolute value of f, j equal 1 to k, minus k times lambda. So I'm defining this quantity for all k in n star, and I want to remark that if we prove that for every n in n star, the measure of the set of all those omega where the maximum of mk lambda is positive for k smaller than n, if we can control that by a constant divided by lambda to the p times the LP norm of f to the p, then we would have the result. All right, just by fatu lemma, you would take a limit of these integrals of indicator function as capital N goes to infinity, and asking for this maximum to be positive is really asking for this divided by k to be greater than lambda. So implies the result by Fatu's lemma. So we really only need to prove an estimate of that form, but obviously we need to do that in a way that does not depend on capital N in order to be able to pass to the limit in capital N. So if there exists a C such that for all n this holds, then this implies the result. Of course, the C should also be independent of lambda, and it should be independent of f. Okay, so what can I say about mk lambda? Well, I could rewrite mk lambda as tf minus lambda plus the sum j equal 2 to k of tjf minus k minus 1 lambda. I'm trying to relate mk lambda to mk minus 1 lambda. Now, if I do that, I get tf minus lambda plus t of the sum j equal 1 to k minus 1 of tj of f minus k minus 1 lambda times the constant function. Okay, and then I need to add that k minus 1 lambda times t of the constant function and subtract k minus 1 of lambda. Now, interestingly, when I do that, here I could factor out the k minus 1 of lambda and just rewrite this as t of the indicator function of all of omega, which is certainly in L infinity, minus the indicator function of all of omega. That's the way I should interpret constant, of course. Here, whenever I write a constant, it's the constant function. Now, t of 1 of omega minus 1 of omega, I want to say that this has to be less or equal than 0 because t is a contraction, right? So t of 1 of omega in sup norm has to be smaller than 1, and this here is a function that is constantly equal to 1. So this has to be less or equal than 0. So this entire thing here is certainly smaller than t times f minus lambda, and my smaller is in the sense of inequalities between LP functions, so f is smaller than g if f of x is smaller than g of x for almost every x, plus t times what's in that bracket here, which is nothing but mk minus 1 of lambda. So this is a induction relation between mk lambda and mk minus 1 lambda. Now we're going to exploit that. Okay, now notice that we can go a little further than that and say that mk lambda is smaller than tf minus lambda plus really the maximum of t of mk minus 1 lambda and 0. And then we could even use positivity and say that this is smaller by positivity than t of the maximum of mk minus 1 lambda and 0. Okay. So now if I look at the integral of mk lambda and I multiply that by the indicator function of the set where mk lambda is non-negative. I can control that by the integral of tf minus lambda over that same set, the set of all those omega where mk lambda f is non-negative. And then I have plus the integral over that same set of t of maximum of mk minus 1 lambda and 0. Okay, all of that is d mu. And now I can use positivity of t again, and I can say that this is controlled by this integral plus the integral of t of the indicator function of the set times the maximum of 0 and mk minus 1 lambda d mu. Okay, now the idea is that you're just multiplying something by 1 or 0, so you're getting something smaller than what you had here with this non-negative number. Okay, so let's go a little further here and use the fact that t is a contraction. So on L1, so this entire thing here is controlled on that set by this integral plus the norm of t on L1, which is smaller than 1, plus the integral over the same set of the maximum of 0 and mk minus 1 lambda d mu. Okay, now this is true for every mk lambda. Well, we can go one step further and control this maximum here by a maximum over an even larger set, which is what we have on the left-hand side here. And so what we would get is that the integral over the set where mk lambda is non-negative of tf minus lambda d mu has to be non-negative, and that is for every k equal 1 to n. Right, so now that tells me something. That tells me that lambda times the measure of the set where mu k lambda is non-negative has to be smaller than the integral over that set of t of f d mu. Very good. So what happens if I look at lambda times the measure of the set of all those omegas such that the maximum of 1 upon k sum j equal 1 to k of t j f is greater or equal than lambda, or actually I should say the maximum of the mj lambda is positive. That's better. So if I look at that, mj lambda being non-negative, well, this is really the disjoint union of sets. And so I can rewrite this as the sum from k equal 1 to n of lambda times the integral of, so what would I get? I would get that this is the integral of tf d mu on the set where mk lambda is positive and the maximum of the mj lambda is mk lambda. Right. Maximum has to take one of this k value, and then on the set where it does take that k value, I apply the inequality star that I have here. Okay, but now I can use Euler inequality in this, and I would get that this is controlled by lambda times the integral of tf times the indicator function of the set where the maximum of the mj lambda is positive. And then using Euler, I get that this is controlled by, sorry, there was no lambda here, and the lambda was there in my inequality, and this has to be controlled by the LP norm of tf times the measure of that set, maximum of mj lambda positive, raised to the power 1 upon p prime. And what does that give me then? I get 1 minus 1 upon p. So I've proven here that lambda times mu max mj lambda positive raised to the power 1 minus 1 upon p prime, which is 1 upon p, is smaller than tfp, which is smaller than fp. Now raise all of that to the p, and we get exactly the inequality that we wanted. And notice that we get it with constant 1, which is definitely independent of everything else. That concludes the proof of this lemma about weak type PP control of the ergodic maximal function. Okay, we're now in the position to prove Birkov theorem. So the first thing we do is that we apply von Neumann theta ergodic or mean ergodic theorem. And this theorem gives us that X splits as the null space of identity minus T plus the range of identity minus T closure. Okay, so as we always do, we look at the two components independently. If we are in the null space, then everything is very simple, because 1 upon n sum j equal 1 to n of tj of f of omega is just f of omega for all omega. Well, or almost every omega. They equal as LP function, so they equal almost everywhere. So for almost every omega in capital omega. So we do have our result definitely on the null space. Now, if I take a G which is in L infinity, and I look at identity minus T applied to G, I get something interesting. I get that 1 upon n sum j equal 1 to n of tj 1 minus t of g of omega for any omega in capital omega. This is going to be, it's a telescoping sum, so this is going to be 1 upon n times Tn plus 1 minus t applied to g at omega, and this is certainly smaller than 1 upon n times Tn plus 1 minus t applied to g in L infinity norm, but t is in an infinity contraction, so this is smaller than 2 upon n times the sup norm of g, and this goes to 0 as n goes to infinity. So for an element of the form identity minus t of g and g in L infinity, we have our result. Now you give me an f that is in the closure of the range of identity minus t. It's the LP closure. We can exploit the fact that LP intersected L infinity, just approximating with simple function, is dense in LP with respect to the LP norm. So we have that for every epsilon, there exists a G in L infinity such that F minus I minus T G in LP is smaller than epsilon, right? Because you can approximate F by something in the range of I minus T in LP, and then you can approximate that I minus TH by an I minus TG with G in L infinity, because T is bounded and LP intersected L infinity is dense in LP. So we are very close to concluding the proof because we know the result for I minus TG, and we know that the F that we care about are well approximated by I minus TG. Now, how do we use this approximation argument? Well, we showed that the Cesaro averages of TG of F have to converge almost surely whenever the Cesaro averages of I minus T of G do. So to run that, we say let H be I minus T of G, give ourselves some natural numbers and some level lambda, and then we look at 1 upon n sum j equal 1 to n tjf minus 1 upon m sum j equal 1 to m tjf in absolute value. Now this is controlled by the supremum of these things. So this is controlled by twice the supremum over all n of 1 upon n sum j equal 1 to n of tj of f minus h, and then plus 1 upon n sum tj of h minus 1 upon m sum tj of h. J equal 1 to n, j equal 1 to m here. Okay, so this means that if I take the lim sup of this quantity as n and m go to infinity, and I look at when this lim sup is large, right? If I'm on a set where I do not have almost sure convergence of the Cheshire averages, then this would have to be non-zero. But the measure of such a set is smaller than twice the measure, than the measure, no, not twice, that's correct. Measure of the set being greater than that. Oh, sorry, then the measure of the set where the supremum of n of 1 upon n sum j equal 1 to n of tj of absolute value of f minus h is greater than lambda over 2. Okay, but we know from 14.7 that this is smaller than, 2 over lambda to the p times f minus h in LP norm to the p, which is 2 over lambda to the p epsilon over p. And that's for an arbitrary epsilon, right? I've just introduced the h here in the computation of this quantity that has nothing to do with h. So this is for every epsilon. And so what we have is that the measure of the set where this lim sup is greater than lambda, sorry, j equal 1 to n, I keep putting my absolute values in the wrong place, is 0. All right, so these lim sup are almost everywhere equal to 0, and we get that these quantities have to converge almost everywhere. And of course we know already that they converge in LP to 0, so they have to converge almost everywhere to 0. And that concludes the proof of Birkov theorem.